Alright, number 43 is asking us to determine if the series converges, and if it does, to what, and it tells us to use the telescoping sum to do so. So recall, for a series to converge, or have a sum, we take the limit as n approaches infinity of the nth partial sum, and that has to converge to s, which is our sum. Now the nth partial sum is just the sum of all the terms of our series up until a sub n. So we're taking the limit of that, and if that converges, then our sum is whatever it converges to. Okay, so let's start off. When we're using a telescoping sum, the first thing you want to do is break up the denominator into two factors. So in this case, summation of n equals 2 to infinity 2, we see that this is the difference of squares, so we can write that as n minus 1, n plus 1, and that's the same thing as what we had earlier. Now from there, we want to use partial fraction decomposition to break that up into two different terms. And this is the sum of this, I just didn't write it, n plus 1. Alright, multiplying over by the denominator on both sides, we'd get 2 is equal to a n plus 1 plus b n minus 1. And then plugging in n equals negative 1, just to find the value of b, we'd get 2 on that side. This term goes to 0 when we plug in negative 1, and the other term is negative 2b. So then b is equal to negative 1, and then plugging in n equals 1 to make the other term 0 out, we would get 2 is equal to 2a, so a is equal to 1. Alright, from there, we can rewrite our sum as two different terms, going from 2 to infinity again, as, let's see, a was 1, so 1 over n minus, that's a horrible one, really is pretty bad. Man, 1 over n minus 1, and then negative 1 over n plus 1. Alright, so this is just an alternative way of writing this, and it's going to be useful for us because we're writing a telescoping sum. So a telescoping sum, s of n, and we're going to take the limit of this thing. Remember, the limit as n approaches infinity. So the first term, well, we start at 2, so we're basically going until the n, right? So we just do as many as we need to. So 1 over 2 minus 1 is just 1. And then minus 1 over 3 for this guy when we plug in 2. Now plus plugging in 3 now, 1 over 2. And yeah, I'm just plugging in 3 there to get 1/2. And then plugging in 3 in the other one, we get 1/4. Carrying on, now we're plugging in 4, I get 1/3. And then plugging in 4 to the second part, I get negative 1/5. Going on a little bit longer, plugging in 5 now, I get 1/4 minus 1/6. I'll do one more. Plugging in 6, I get 1/5 minus 1/7. Okay, and then we have all the way up until 1 over n minus 1 plus negative 1 over n plus 1. So that's our nth partial sum, and we could keep on writing out terms, but what we're looking for is for stuff to cross out. So the negative 1/3 and the 1/3 cross out, the 1/5 and negative 1/5, negative 1/4 and 1/4, and if we wrote out one more term for n equals 7, well, we'd have 1 over 6 minus 1 over 8, and then the 6's would cross out, and we could keep on going, keep on writing out terms, but basically the moral of the story is anything after this point is just going to cross out with a subsequent term, because this covers pretty much all integers after a certain point, and this does as well. So after, I mean, they're shifted a bit, but they do all cancel each other out. So we're really just left with the limit of s sub n as n approaches infinity is equal to 1 plus 1/2, and then the last few terms that don't cancel out, right? The nth term. But we take the limit of those things, if we take the limit of that, as this gets really big, this goes to 0, and so does this. So we're just left with 3/2. So the sum of this series is 3/2, and it does indeed converge to that.